Well, hello. Welcome, everybody. It would have been great to be able to attend the conference in person. It's always great to visit Japan. But I do hope that these times find everybody and their families safe and well. And I'm hoping that you are enjoying a good conference. So what we're going to discuss in this presentation is a focus on Aurora, with some thoughts about how Aurora fits into our bigger picture and where we are driving HPC in the coming generations using Aurora as an example. So with that, there's just a few disclaimers that I'm sure you've seen if you've seen Intel presenters before, and we'll get right into it. So before we start talking about Aurora, let's talk about the three pillars of exascale. And it's important that we think about these three different pillars because really in the last decade, the face of HPC has changed. It used to be just simulation as depicted on the left, but as we all know over time, now HPC really is the combination of simulation, big data analytics, and artificial intelligence all coming together to work in a tightly coupled set of workflows to bring greater revolutions, greater insights to science, as well as new discoveries, faster discoveries to the engineering fields. So it's really important as we go through this presentation to keep the realization that a lot of what we've driven in Aurora, and certainly what we're thinking about going forward, is all part and part of the fact that we're looking at these three pillars coming together. So this is a great example of a good colleague of mine, Bill Tane, from the Princeton Fusion Lab. And I remember conversations with him 7, 8 years ago when he was working on a particularly difficult problem about trying to figure out any of the escapes in this plasma toroid. And I remember the conversations because we were talking about exascale at the time. As we all know, we've been on that for about a decade. But in the conversations, Bill was telling me, oh, we're going to need more than a zettascale of computing to actually, from a grounds up, simulate and make sure to catch all of these different escapes that might happen in the hot plasma toroid. But an interesting insight that he and his team realized, and I think it really just demonstrates the power of what I talked about on the previous slide, which is using all of these together. They came up with this idea of throwing AI learning at the problem, and they were able to solve it. And as you see by the Nature paper, they were able to solve it with petascales of computing. So 4 to 5 orders of magnitude less of computing. And to me, this demonstrates what we talked about on the previous slide about how these are all coming together. And so if we go forward, then what we're really talking about doing is today, if you take a look at what you see over there, we talk about the three different pillars: the simulation, the big data pillar, and the AI and machine learning pillar. And there's been a lot of great work that's been done today to be able to utilize all of these pillars in a given workflow and be able to utilize pieces of information, insights that are coming from one pillar to the other. Oftentimes, though, it's a sequential thing. And what we're envisioning with Aurora is what you see here depicted on the right. And that is using some technologies that I'm going to describe as we walk through this presentation. We really envision a much tighter coupling and a much tighter integration of these three different pillars with significantly more bandwidth and significantly higher productivity in being able to utilize all of the frameworks that you see here depicted in the big data, simulation, and AI and workflows all coming together. So hopefully with that context as background, when we walk through some of the discussion on Aurora, and I get a chance, an opportunity to tell you what it is we're doing, it'll make sense as to what we're accomplishing with that. Okay, so let's walk through. So if you had a chance to see Exascale Day or some of this, or some of the presentations around that time, about in early October, you'll recognize some of this. But it's it's amazing just to take a step back and think about really what an exascale of computing is, and what Aurora will be when we achieve that exascale of compute. The first one, just to get our heads around it, is if you think of a standard problem, right? Think of like 1024 and 354,000 times an equivalent number. If everybody on Earth, all 8 billion-ish people, did that, and they were able to punch it into a calculator once every 10 seconds, what you would find is that it takes 40 years for all of us to be able to do something that Aurora will be able to do in just 1 second. And it's when you put it that way, we all know what an exascale is, right? It's a quintillion, a billion, we've seen those numbers. But when you just really think about the amount of computation that goes in and how much can be accomplished in a short period of time, and then you think about providing this machine to scientists to use over time. And there's a lot of other very interesting facts as well, that I won't go ahead and read through. But let me just focus on the second to last one, which is there's a massive amount of data, and I'm going to talk about Deos, and I'm going to discuss how we've integrated Deos into the high-speed fabric. But that allows us to achieve that second from the bottom interesting fact, which is that in 8 minutes, Aurora will be able to store enough characters to write a stack of books that would reach to the moon. Again, just a massive amount of data, which is becoming clearly the cornerstone to how we do computation. So let's move on to the next slide. And I'm going to on the successive slide, I'm going to talk in a little bit more detail, but this pulls it all together in one picture, at least what the node looks like. On the next slide, I'm going to talk about the system architecture, and there'll be a lot more. But this is a nice sort of summary of this. And again, when I get to the system architecture slide, we'll dive in a little bit more into each of these details. Okay, so let's move to that slide. So taking a look at Aurora from an overall systems perspective, right? We have the standard large number of compute racks that are all interconnected with a high performance fabric. That will be greater than an exaflop of sustained computation as measured by LINPACK. But the interesting thing that's worth noting at this point is, and for the folks who have been following the Aurora project and who also followed Coral, which was the Coral and the Exascale initiatives in the United States, which is what Aurora came out of. In addition to that sustained exaflop of compute, we also, and this just goes to those 3 different pillars that I talk about, Aurora will be responsible for delivering 50x in performance over geo mean of applications in each of those 3 different pillars over what was at the time Coral went in for RFP, the top systems, which was Sequoia and Titan. So it will be 50x in simulation and modeling, 50x in AI, and 50x in big data and analytics. In addition to those large number of compute cabinets, we also have a significant amount of high-speed storage, and I have a architectural diagram of this coming up, but depicted by those orange racks that you see in the right of the figure. These include Optane for persistent memory, and there's over 230 petabytes of storage that is accessible by Deos. as well as achieving rates of greater than 25 terabytes per second. If we break down what a rack looks at, what you'll see in each of the switch blades is that we have an HPE slingshot connected in a dragonfly topology for that high performance fabric that I talked about. And then each compute blade consists of both an Intel Xeon as well as an Intel GPU X to the E. And the X to the E, as if you've been following all the news, uses both integration, uses both tight integration, uses integration technology, both EMIB as well as Foveros. The Ponte Vecchio, that's the code name for it, that was announced last year at Supercomputing, has unified memory, uses PC and uses PCIe. The Xeon it's part of the Xeon scalable line, and it's a Sapphire Rapids based processor. There's 2 of those per node, and then there are 6 of the Ponte Vecchio GPUs, and they are, as was depicted on that figure in the previous chart, they are all interconnected. The GPUs, that is to say. So it provides the ability to exchange data rapidly without the CPU needing to be involved. Okay, so let's take a look at what Aurora offers from a software perspective. So a lot of the partnership, a lot of the great partnership that, that we've had with Argonne is to take a look at what we're going to need to do in this exascale era in terms of achieving high performance and scalability. So the first one is an effort called MOS, and this has actually been a great partnership that we've had with our collaborators at RIKEN, Professor Ishikawa-san, as well as Bouaj Darofi and many others. The MOS team and the team at RIKEN have partnered very closely on this. We've leveraged off of each other, but let's talk about a little bit about what MOS is. Typically, or there's been 2 approaches historically to designing operating systems for large, scalable, high-performance machines. One of them has been to start with a lightweight kernel. Another of them has been to start with Linux and try to strip it down. And if you start with a lightweight kernel, one of your goals is to try to get as much Linux capability. And if you start with Linux, as you start removing some of the things to allow it to scale, your goal really is to try to keep it as much Linux as you know, not break that Linux compatibility that you're starting with. And what MOS does is it recognizes the fact that we have lots of CPUs and lots of cores. And what we do is we run both a Linux on one or more of those CPUs, and we run a lightweight kernel on the rest of them. And this allows us to achieve high performance for the applications that are running on the CPUs, but with a full Linux compatibility, because if there's a call that the lightweight kernel doesn't implement, because Linux is on the same node in the same shared memory domain, we can make the Linux call. A second realization that came out of these machines is that when you're running and you have these large number of racks and nodes and GPUs and everything, that what you need is a scalable way of monitoring the machine, of figuring out what's going on. And we have something called a unified control system, which is depicted there in the bottom right. And what it shows is that for all of the different subsystems in the machine, across the service nodes, across the network, across the compute nodes, of course, there's a single unified database scheme that you can, that the user can, that the online software can, or that offline software can query and get information about. And all of this information is stored in a common, consistent manner and can be queried historically and offline. We, of course, continue to focus on MPI as well. Obviously, that does remain a cornerstone. And then the fourth bullet down is Geo, and that's for our power manager. Clearly, as we have moved into the as we are moving into the exascale regime, what you find is power is becoming more and more important. And what Geo allows applications, users to do is to either achieve for a lower energy, a similar equivalent performance by keeping track of where the MPI tasks are and accelerating or decelerating them or the cores that they're on, or to achieve a higher performance if you're not trying to cap the power. The fifth technology that we're working on is something called PMIX. And PMIX originally started just as a way of being able to launch jobs really, really quickly. It was called Instant On, but over time, PMIX has grown into a much larger communication agent between the system management nodes as well as the applications. And then Deos, which I mentioned before, I have a slide coming up that I will talk about it on. And so here's the architectural diagram that I had discussed earlier. What you see is in this, in that light gray square that's sitting above the racks. The gray racks or the white racks are the compute racks, but the orange racks, if you remember that the chart that I showed you before, are the Deos nodes. So what's important to recognize is the fact that the Deos nodes are sitting on the high performance fabric. And what that allows us to do is we now have, as I indicated, a massive amount of storage that is on the high performance fabric and effectively looks like, functionally, it looks like it's just NVM that's sitting on your node. But because the high performance fabric is connected to it, it allows it all to exist in one place. And this is the storage that Deos utilizes. So let's talk a little bit more in greater detail then about what Deos is. So first of all, Deos is Distributed Asynchronous Object Store. And you know, one of my favorite stories that I like to talk about, when I met Shohan Lombardi, who's the lead architect for Deos, years ago, and we talked about why he was undertaking this effort. The interesting thing that really stuck out to me is that you know, for folks like myself and perhaps some in the audience who've been in computers and for a long time, you know, years ago we optimized file systems so that by the time that slow spinning platter came around, and everything was absolutely optimized to take best use of the head by the, you know, as you started reading the data. But storage has changed, right? As you see depicted in the figure, we're no longer using hard drives for storage. Instead, we're using products like Intel Optane or non-volatile memory. And what that means is that historically, 99% of the lifetime of a bit was spent waiting for the platter to come around, i.e. in hardware. But today, with the same file system stack, 99% of the time is spent in software. So we no longer have the right optimization point. And this was one of the realizations behind Deos, is that we can do a lot better. And they have benchmarks that show, and if you looked at the supercomputing results where they achieved #1 in the IO 500 and things like that, they have benchmarks that show, you know, 3-4 orders of magnitude improvement, especially on the small small read IOP type operations. It was, of course, recognized the fact that the data, this new type of storage, can be random access, and you can access it in small, in very small pieces. So in addition to that, though, and this is going to tie into the story I talked about in terms of bringing everything together, Deos provides object store, and it provides a productive way of allowing these 3 different architectures to all work together. Okay, so all of the activities that we are doing, in case folks have not heard about OpenHPC, are all those 6 different pieces of software are open source. So if there's any interest in them, please feel free to reach out and I can connect you with the architect, or we can talk more. And many of them, it is our intent over time to contribute them to Open HPC. And some of them actually already are in Open HPC. So Open HPC continues to be an important effort for us. It's a way of getting a lot of the great technology that not only we are working on, but that others are working on out there to the community. So let's come back to this picture here. I talked about it at the beginning when we said, you know, today we're on the left, and where we want to move is over there on the right, where we are bringing them all together. And one of the stories on how we're doing that is by using Deos, right? It provides very high bandwidth between the pillars, and it also provides a new object model which allows the workflows from these different pillars that you see on the right to easily share data in a productive manner. You don't have to linearize it through a file system. Instead, you can just pass the pointer to the object. There's another piece to this story, and that is, how do we get these all working together? And one of the other types of efforts that we are working on in Aurora is taking the workflows from these different pillars and tightly integrating them. And so let me describe a little bit of the work that we're doing with Spark. So Spark is from the big data analytics pillar, and it grew up in the Hadoop model for folks who are not familiar with it. And it's a very sort of robust way of managing distributed computing. And when you apply it to, or when you try to apply it to supercomputing, what you'll find is there's many places to allow us to optimize this and more tightly integrate it. And so as part of Aurora, we are undertaking tasks, and this is just an example. We're doing this in the AI space as well. And I'm not going to walk through all of this, but a couple things we are doing is integrating the scheduler within Spark into the overall resource management system of Aurora, which is COBOL, which is based on PBS Pro. We are also editing the task scheduler, or modifying the task scheduler to make sure that it's NUMA aware. And we are utilizing the Deos technology to be able to allow us to much more rapidly exchange information during the shuffle, as well as just for when we offload the data. So where are we going, right? Why, you know, I talked about these 3 different pillars. And just stepping back now for a minute, where is HPC? Where is computer science going? One observation I think that a lot of people would make is that heterogeneity is really becoming the challenge of today, right? In the 90s, we went from when there were lots and lots of you know, microprocessors all being connected. Then in the 2000s, we went to where there was, you know, massive numbers of nodes. And today it's heterogeneity, and it's not just in the hardware, right? Obviously GPUs are playing a big role, but there's other compute, right? If you take the Intel taxonomy, there's vector, scalar, spatial, as well as matrix computing, right? And more these are all going to play a part. But it isn't just in the hardware; it's in the memory, it's in the software ecosystem, and there's new types of compute that are coming in. AI, we've talked a lot about, clearly. Edge is something we haven't talked a lot about, but it's absolutely the case that Edge is playing a greater and greater role in HPC. And more, there's a lot of energy and effort being driven into AI and cloud. And so, you know, if you pull all of these together, it's clear that HPC is becoming more and more complex. And so how are we at Intel addressing these? I think Aurora lays out a really good framework of that. It shows you concretely what we're doing to deliver in 2022, that exascale machine. And it shows that you really need a system design methodology. Aurora has been co-designed with the software teams, with the hardware teams, with our very key collaborator, Argonne. as well as tightly done with our subcontractor HPE. We've also leveraged, for example, the work that Intel was already working on for GPUs. And we're also working at pulling the different types of components, and we believe that going forward, we need to do this even more in together at the right level. And as folks who have seen a lot of the announcements, we now have a one API goal, but we recognize the fact in a heterogeneous world that we need to provide a productive way to allow programmers to be able to span across each of these different types of compute in a way where they can speak the same type of language, the same thing, while you might need to do additional optimizations for the type of compute that you're on. One API provides this way to span across heterogeneous computing. And so Intel definitely believes HPC is onward, upward, and continuing to go. We have ways of continuing to facilitate platforms for HPC, AI, big data, and Aurora is a great first step in that direction. So with that, I just wanted to say thank you very much. I would have, again, loved to have been able to be here in person and be able to interact and take questions. I do hope that in the future, as travel permits, we will be able to do more of these in person and get a chance to interact. It's a shame we won't be able to take questions, but if anything here excited you, or if you'd like to hear more about it, please let me know. I'm happy to take questions by email, and I sincerely hope that you have a good rest of the conference. Thank you.